Welcome back to another exciting episode of Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by the brilliant Victor. Before we dive in, I just want to remind our amazing listeners that if you're enjoying our content, please rate us on your podcast platform of choice. Your support means the world to us.
Thanks, Sheila. And yes, a big thank you to all our listeners out there. Your feedback helps us improve and reach more developers interested in decentralized applications.
Absolutely. Now, let's get into today's topic. We're currently in Season 1, Chapter 5, focusing on networking in P2P systems. Today we'll be discussing NAT Traversal techniques. But before we start, I have a quiz question for our listeners. Victor, would you like to do the honors?
I'd love to. All right, listeners, here's your quiz question for today. What percentage of internet-connected devices are estimated to be behind NAT? Think about that as we dive into our discussion, and we'll reveal the answer at the end of the episode.
Ooh, that's an intriguing question. I'm curious to know the answer myself. But before we get too far, Victor, could you explain what NAT is for our listeners who might not be familiar with the term?
Certainly. NAT stands for Network Address Translation. It's a method used in computer networking to map multiple private IP addresses to a single public IP address. Think of it like a receptionist in a large office building. When you call the building, you don't directly reach individual offices. Instead, the receptionist directs your call to the right person.
That's a great analogy. So, in this case, the receptionist is like the NAT device, and the offices are like the devices on a private network, right?
Exactly. You've got it, Sheila. The NAT device sits between the private network and the public internet, translating addresses as needed.
I see. But why do we need NAT in the first place? It seems like it would be simpler if every device just had its own public IP address.
That's a great question. NAT was actually introduced back in 1994 as a solution to the limited number of available IPv4 addresses. IPv4 is the fourth version of the Internet Protocol, which provides unique addresses for devices on networks. By allowing multiple devices to share a single public IP, NAT helps conserve these addresses. It also provides an additional layer of security by hiding the internal network structure from the outside world.
Fascinating. But I can see how this might cause problems for peer-to-peer systems. If devices are behind NAT, how can they directly communicate with each other?
That's the crux of the issue, Sheila. NAT makes it difficult for external devices to initiate connections to devices behind NAT. This is where NAT Traversal techniques come in. The three main protocols we use for this are stun, turn, and ice.
Stun, turn, and ice. Those sound like fun acronyms. Can you break them down for us?
Of course. Let's start with stun, which stands for Session Traversal Utilities for NAT. Stun is like a mirror for your network. It allows a device behind NAT to discover its public IP address and the type of NAT it's behind.
So stun helps a device figure out how it appears to the outside world?
Exactly, but stun has limitations. It doesn't work with all types of NAT, particularly symmetric NAT. That's where turn comes in.
And what does turn stand for?
Turn is traversal using relays around NAT. Unlike stun, which helps with direct connections, turn acts as a middleman. It relays all traffic through a turn server. It's like having a mutual friend pass messages between two people who can't directly communicate.
I see. So turn is more of a fallback option when direct communication isn't possible.
Precisely. Turn ensures connectivity in almost all network scenarios, but at the cost of increased latency and server load.
Interesting. And what about ice? How does that fit into the picture?
ICE, or Interactive Connectivity Establishment, is like the conductor of an orchestra. It coordinates the use of various NAT traversal techniques, including stun and turn. ICE tries multiple methods to establish the best possible connection between peers.
So ice isn't a specific technique, but more of a framework for using different techniques.
That's right. ICE typically starts with the most direct and efficient method, like stun, and falls back to more reliable but potentially slower methods, like turn, if needed.
This is all fascinating, Victor. But I'm curious, how do developers actually implement these techniques in their P2P applications?
Great question. Many programming languages and frameworks have libraries that implement these protocols. For example, in JavaScript, you might use the simple peer library, which handles ice, stun, and turn behind the scenes. In Python, you could use the aortc library.
That's helpful to know. Are there any common pitfalls developers should be aware of when working with these techniques?
Absolutely. Let me share a couple of important points to keep in mind. One common mistake is relying solely on stun and not implementing turn as a fallback. This can lead to connection failures in some network environments. Another issue is not properly securing turn servers, which can be exploited if left open.
Those are important points to keep in mind. Before we wrap up, do you have any fun facts about NAT Traversal you'd like to share?
As a matter of fact, I do. Did you know that the first NAT RFC, request for comments, was published in 1994? That's nearly 30 years ago, and we're still using and improving upon this technology today.
Wow, that is interesting. It really shows how foundational these technologies are. Now I think it's time to reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The question was, what percentage of internet-connected devices are estimated to be behind NAT? The answer is approximately 80–90%. This high percentage underscores just how important NAT traversal techniques are in modern networking.
That's a staggering number. It really puts into perspective why understanding these techniques is so crucial for P2P developers. To summarize what we've learned today, point 1. NAT allows multiple devices to share a single public IP address. Point 2. Stun helps devices discover their public IP and NAT type. 3. Turn provides a fallback relay option when direct connection isn't possible. 4. ICE coordinates the use of various NAT traversal techniques to establish the best possible connection. 5. Implementing all these techniques is crucial for robust P2P applications.
Excellent summary, Sheila. I hope our listeners found this deep dive into NAT traversal techniques informative and useful for their P2P development journey.
Thank you, Victor, for sharing your expertise with us. And thank you to all our listeners for tuning in. If you enjoyed this episode, please remember to rate us on your podcast platform. You can also visit crashcasts.com to join our Discord community or support us on Patreon. Until next time, happy coding.